Hello world. Thank you, Lutico. And just for clarity, we'll take that one out. So a function of x that looks like x to some power n, and now this is actually, it's not x not equal to 0, it's n not equal to 0.
Oh yeah, A, not X.
Right? So not this one, but that one. So this works when for any power, n can be a positive number or a negative number. It can even be a decimal number. Yeah? Just not 0. And then this is what you do. To get the derivative of a power, you take the power, you multiply it in front, and you reduce the power by 1. Right? So you've correctly used this rule here, but this 2 and this 3 don't go there. What should go in here? X. These are functions, right? As soon as you put a number in the function, you're saying, now give me a specific number back, right? If I tell you, if we have a graph and we have a function, and if this is a function f of x, so it says for any number x, I can tell you what the value y will be. Yes? For any input x, if I choose this x, then this is the value that comes out. This is the y, if that's the x. But now, if I say, what is f of 2? Let's say this is 2 here. Now, the answer is, I don't know, 5, maybe? F of 2 equals 5. F of 2 cannot be a function.
Why? Why?
It has to be a value. If you tell me I want this input value, then I have to give you the output. That's what the function does, is you give me an input, I give you an output, one value. Yeah, that's what a function does. So when you're still writing with x's, then it's a function of x. The function is x squared. The function is x cubed. Yeah? So just notation here. So that's important. Okay, so that's the power rule. And we can do a few more examples. So let's write f of x here, and then f prime of x here, and we can make like a table. So we started with, we'll start with x squared, x cubed, x to the 4th, and then we can do, actually, sorry, I'm gonna start it here, and you'll see why. X squared, x cubed, x to the 4th. Right? So we've done x squared. We know that you take the 2, you multiply in front, and you reduce this by 1. So 2 minus 1 is 1. So this is 2x. Fine. X cubed, what do we do? 3x squared. What about for x to the 4th? Okay. And we can see how the pattern will go, right? Now let's go x to the minus 1. So actually, I'm going to write x to the 0, but we're not going to do it yet. X to the minus 1, x to the minus 2. We'll skip x to the 0 because we said n is not allowed to be 0 for this rule. Actually, we have to do x. So x by itself When you apply this rule, what do we get?
X.
We apply the power rule to x. What do we get as the derivative? It does exist. So let's apply. So we have to remember, like you said, this is x to the 1, right? Okay. So 1 times, so we're going to delete it because 1 times doesn't mean much. And then x to the power 1 minus 1, which is 0. Okay. So we have 1 times x to the power 0, which is what? X to the power 0 is 1.
1.
Anything to the power 0 is 1, right? So then we have 1 times 1, which is, so this is just 1. So notice we're going x cubed, x squared, x, no x. We keep subtracting 1 power. So this is, the derivative of x is 1, right? And we can remind ourselves, if we do a quick graph, so if I have f of x, which is just the straight line, f of x equals x, right? What is the slope of this line? First, it is a line, so the slope should be constant. We expect that the slope is the same everywhere, right? If the slope is the same everywhere, then it's a constant, which means the derivative must be a constant, so it can't depend on x. The slope should not change as I change x. The slope here is the same as the slope here, is the same as the slope here. Everywhere it's the same slope, and specifically it's the slope 1. So if I go 1 unit to the right, how much does y change? So if I go from f of 2 to f of 3, how much, what is the difference in the value? 1, yeah? That's what the slope means. So this makes sense, right? That this would be the derivative? It makes sense? Okay. So now, I said we'll skip x0 because we said this is not the rule for x0. Let's do x minus 1. So we apply the power rule to x to the minus 1. What do we get? Negative x to the minus 2. Minus 1 minus another 1 is minus 2. And how about this one? So we have minus 2 in the exponent, so I'm going to multiply in front, yep, minus 2, times x to the power, minus 2 minus 1 is minus 3. Okay, and so on. It's simple, right? Okay. Now, you might ask, what about x, this is not in the sequence now, but what about x to the 0.5? Sometimes we have, right? This is the square root. Remember, this is a fractional power. This is 1/2. X to the 1/2 is the square root. So let's apply the power rule again. So we have 0.5. We're going to multiply it in front. So we're going to have 0.5 times x to the power 0.5 minus 1, which is negative 0.5. Exactly. It works just the same. For any decimal power, you just do the same thing. So the power rule works for any number n, not just integers, any number except 0. Now let's find out why it doesn't work for 0. Right? What is x to the 0? It's 1. Yeah? Just the number 1. Now think of the graph of f of x equals 1. F of x equals 1. What does this graph look like? What does f of x equals 1 look like? It's a straight line. It's a straight line. Is it an angled straight line? No. It's vertical? A vertical line, can a vertical line be a function? A vertical line cannot be a function. Remember? This is a horizontal line. Equal 1. So just a reminder, what does this say? It says, give me an input x, any number you want. And the answer, so 2. Okay, so if I go to 2, the answer should be 1. You will give me the answer 1. Okay, so at x equals 2, I have 1. Give me a different number. 7. If I put in 7, the answer should be 1. So at 7, I go 1. Give me another number. So if I have 3, the answer should be 1. So I go up to here. Now all these points, now no matter, I hope you see the pattern, no matter what x you choose any x you want, the answer will be 1. So you end up with a straight line, a flat line. Yeah? This says no matter what x you choose, the answer will be 1. Okay? Now if it's a flat line, what is the slope of a flat line? The slope. The delta y over delta x is 0. Why? It's never going up or down. The change, no matter what delta x you choose, there will be no change in y. Delta y will always be 0. Yeah? So here, the derivative is 0. Yeah? Now, in doing so, we have actually, so we've answered what is the power rule. We have now discovered the constant rule. If I have a constant, 1 is a constant, right? A constant, what is the derivative of a constant? It's 0. So it doesn't matter that the number is 1. I could change this to any other number. This could be f of x equals 3. So I change, the line would go here, but it's still a flat line, right? It's just a different height, but it's still a flat line, which means the change in y, no matter what x I choose, there is no change in y, ever, for a flat horizontal line. So for a horizontal line, the slope is always 0, the m is 0, and m is it's 0 everywhere. For all x, m is 0, and so the derivative is 0. And this is true, so it's true for x to the power 0, but even more, it's true for any constant a. Or maybe let's use c for a constant. For any constant c, for any number, when there's no x, just a number, yeah, and whatever the number is just says how high is it's a horizontal line at some height. It could be negative, positive, right? But the derivative of that horizontal line is 0. Because the line has a slope of 0. Okay? So we have 2 of our rules, the constant rule, the power rule. We're going to take out these examples now, thank you. And we're going to go on to, so we'll keep that, because that's important. Let me just move this down. So the constant rule says that the derivative of a constant c is the derivative of a constant is of 0. 0. Okay? The derivative of a constant is always 0. So let's look at the sum and the difference now. I'll take this one out. Huh? Yeah, ask, please. The constant rule? So if f of x, if f of x is some constant c, where c is a constant, okay? A constant, sort of any real number. Any real number, so C, another way to say that is C is an element of the real numbers. This is the set of all real numbers, R. Huh? When I have this, then the derivative of f is 0, if f of x is a constant. So I could replace f by c, which is what I did here, and the answer is 0. Now I've just rewritten it in different words, but do you want me to explain why it's 0 again? Yeah? Can someone try to explain? Why is this true? Why is the derivative of a constant function 0? So, one, we need to remember. Can I erase this one now? Yeah. Use the space. So we want to remember that the derivative, right, we motivated, why are we interested in a derivative? What is this thing called a derivative? Why should I care? Yeah? And it came from the question of, when I have a graph of a function, if the function is a straight line, it's easy to calculate the slope, right? But if I have a function that is not straight, then what does it mean to have a slope of this function? How do you calculate a slope? And we... Please. What were you going to say?
You said we use a secant line.
A secant line? Okay. So maybe a line like that. And then?
Change y. Change x.
So I choose a point P, and then another point, maybe Q. And I ask, what is the slope of the line PQ? And it'll be some delta y over delta x. And then I said, but this is a straight line. The secant is a straight line. So it has a slope, right? I have 2 points, I can calculate the slope of this line. But this straight line doesn't look like the slope of the curve at P. Yeah? Where the function is, this is going down, and this line is going up. So that can't be the same. So I say, okay, let's take the secant closer. Let's take it here. So again, it's a straight line. So I have a new, this will be Q2. This was Q1. So I use Q2. Okay, that's getting closer. Now at least it's a line going down. But it's still not exactly the tangent, right? The tangent at P is this line. And the question is, I want to know the slope of this line. But I only know one point P. Because all I know is the function, right? All I know in terms of numbers is the numbers on this line. I don't know any other numbers. And I can't imagine them, I can't fake it. I mean, you could draw it on graph paper and you could estimate, sure. But in a formal way, how do you get the exact value? So we said, well, if we take these secant lines and we bring this point, Q1, Q2, and we come closer and closer and closer to P, right? We keep drawing secant lines. They get smaller and smaller, but they're always a straight line, and it's always 2 points. And I can calculate the slope in each case. For every Q2, then I have a Q3, then I have a Q4, and they get infinitesimally close to P, but not exactly at P. So I always have 2 points, and I can calculate the slope. Delta x will be very, very small. Delta y will also be smaller. And then I write down, I start saying, okay, for Q1, the slope was some number, let's say 2.3. And then for Q2, the slope was 0.3. At some other point, the slope was minus 0.5. At another, so these points are getting closer and closer to P, right? Now the slope that we would calculate would be minus 0.666, and then another point would be, M would be minus 0.68, minus 0.69, minus 0.699. And all of these are points that are getting closer and closer to P. Okay? What would we then conclude about the slope of the tangent line at P? The line that doesn't have a Q. If you look at these numbers, are they approaching something? What? What are these numbers getting closer to? Negative 0.7. Maybe we're not sure yet. We would want to do a few more. We could do that and see, are these numbers getting closer to something? In this case, minus 0.7. So then we would say the slope of the tangent at P is negative 0.7. We did not calculate it. We don't get the slope of the tangent from doing this. We can't do this because we don't have 2 points. We only have 1 point, the point P.
So there is as Q approaching P is zero.
So what we're doing is we're taking a limit. That's why we started with a section about limits. We're saying the limit as this distance between P and Q, right? The Q has an x value and the P has an x value. As this distance gets smaller and smaller, the Q's are getting closer and closer to P. And I'm calculating this, which is the slope, right? So I calculate these numbers. The limit of doing this gives me 0.7. But I can't actually use this formula to calculate the slope of the tangent line at P because I only have 1 point P. And to use this, I need 2 points. See? So I can't calculate it here, but I can calculate everything getting very close to it. And then if I see, okay, everything is getting closer and closer to this number, then that number must be the value that I'm looking for, which is the slope of the tangent. In this case, the minus 0.7. Right? If I keep doing this, I will never get minus 0.7. I can take all the Q's, you can go a million Q's, very close to P. You will never get minus 0.7. But you will see the numbers getting closer and closer and closer to minus 0.7. So by looking at it, we say, aha, this is getting closer and closer to this. So this is the number I want for the tangent itself. Yeah? This was our motivation, the first motivation for what is this thing called a derivative. And just to close the loop. Okay, so I don't need these now. So I will write. So we've convinced ourselves, in this case, we're not yet talking about a derivative. All we were saying is, what is the slope of the tangent? Right? First, are we clear what is a tangent line? Yeah, we're talking about tangent lines and secant lines. We need to be clear about the difference. What is the difference between a tangent line and a secant line?
Secant line has 2 points.
The secant line has 2 points.
Tangent line, that is the action towards.
So the tangent line touches the function f, touches f at 1 point only. Here it crosses at 2 points. Ishmael is looking. We're together? Okay. So the tangent line touches, so if ever you forget, just remember, this is a tangent line. My head is a curve. If I put a straight line on this curve, it will only touch at 1 point, my head. Okay? And the slope of the line that is touching my head at 1 point, at this point, that slope is what we call, well, this line is the tangent line, and the slope of that line is the curving of my head at that point. Of course, if I move it, then the slope changes also. Yeah, here the slope is different. Here it looks flat. Here it's going down. Now it's going down less and less. Now it's flat. Now it's starting to go up. Yeah, so where you are, imagine this is a function. Where you are on the function, which value of f of x, right? So if you're at this x, or this x, or this x, you have a different tangent with a different slope, right? And now you say, okay, so I know how to calculate, I know how to find the slope of the tangent at 1 point. I can do this whole procedure, yeah? But now someone comes and says, look, I want to know the slope of the tangent at any point. And I don't want to have to go through this whole procedure. In other words, I want another function, right? What does a function do? A function says, give me a value x, I will give you an answer. So we have the function, but now I say, that's fine, you have a function. The function is the curve of my head, yeah? But now I want a different function. I want a function that will tell me, at this value x, what is the slope of the function here? Not the value of the function is the height. Here it's at, let's say this is 0. So here it's maybe 10 centimeters, 15, 20 centimeters, 15, 10, right? If I need more space. I'm going to erase this one. I can rewrite it later. I have a function f of x that looks like this. So here, maybe it's worth 10, this is 15, this is 20, right? 15 goes there too, and 10 goes there too. This is the function, and this is the axis x. So this is something like Amgad's head, okay? So what the function does is if you tell it, here is an x, where am I? You say, the height of Amgad's head is now this number. But then I say, yeah, that's fine. But what I really want to know is, there's a tangent line at this point. What is the slope of that tangent line? And what is the slope of the tangent line at this point? At every point, everywhere on the function, there is a tangent line. And every tangent line is different. It has its own slope. And you would like a function that tells you the slope of the tangent line at any value x, right? So we want a function, I'm going to write fn for a function that tells us the slope of the tangent line for any value x. So the procedure we did earlier with the table of numbers, that was for one value of x. And you could do it for another one and another one. But doing that will never give you a function that for any value x, this is the answer. And now what we want is a function that tells us not the value of the function, these are the values of the function, but the slope of the tangent line at every point x. That's what we want now, okay? And that function, this new function that we have said we want, this function we call the derivative. This is what we call the derivative. And in particular, if you look at the word derivative, you might see that this comes from the word derive. To derive is to make it from something, yeah? How do we make cloth for our shirts? It is derived from cotton, maybe. How do we make steel? It is derived from iron and carbon and something, right? It is made from. So we derive this function from the original function. So the derivative, because of course you can say, well, if I change the function, if I pick a new function f of x, the tangents will also change. They will be different. So now my derivative for a new function, like this one, this is a different function from this one, right? And for the same value x, if I choose x equals 1, here the tangent looks like this. Here, if I choose x equals 1, the tangent looks like this. Well, this line and this line clearly have different slopes, right? So the slope of the tangent depends on the function. And so the function that will tell us the slope of the tangent for any value x depends on the function itself. It is derived from the function itself, and therefore we call it the derivative.
Slope of that f of x is 450.
What is this slope? We don't know yet. We haven't calculated.
So because I don't know how to find so using that tangent line. What I know is by using
Yes, correct.
So is this okay? Because you have only 1 point tangent line. So you say it depends
on the function. So now with this function, I would do the same thing that I did here. I will take secant. So I will start at my point P. This is the point that I'm interested in. I want to know what is the slope of the tangent here. So I will draw a slope, right? But clearly this slope is not the same as this slope. So let's make it better. Let's go here, Q2. Okay, it's better, but it's still not the same. So I keep coming closer and closer. I take a Q, this Q2 was here, this Q1 was here, this was x of Q1, this is x of Q2. I could take a Q3, Q4, Q5, Q6. I get closer and closer, and my secants will get shorter, but you can see the slope of the secants is getting closer to the tangent. It will never be exactly the same, but it will get closer. And that's what we meant by saying we take the limit. We calculate the slope of all these secants, and we make a list, and we see, is this list approaching something, a value? Does it have a limit? Does that sequence of numbers have a limit? If it has a limit, that limit is the slope of the tangent line. Right? But doing that procedure works if you've already chosen a point P. What we want now is a function that will give me the answer for any value x without having to do this whole sequence of values, taking all these secants, right? So we said, okay, we know this. So I'm going to write this again in a different form. To show a bit more the connection to the derivative. So what we want to recognize clearly is the connection between the derivative and the slope. And that the derivative is a function that tells you the slope of the tangent anywhere. So we started by learning how to find the slope of the tangent at one point. Now we're making it bigger. I want the slope of the tangent at any point. How do I do that, right? So we took this and we wrote, you will remember, we had, so the limit part is the same, but then we wrote something like this, f plus delta x minus f of x divided by delta x. You remember this from last week? These two are exactly the same thing, just written in different ways. I want to pause and see, do we appreciate that these two are the same? Or should we demonstrate again? Yeah, it's not clear why these are the same? All right. So, it's mostly a matter of notation. Yeah? Do you think you can show?
Sure.
You think? Come try. There's a lot of value in trying, even if you end up missing something. Oh, do you want the mic? Just talk.
I'm just trying.
It's okay. But so they can hear if you're talking.
Just trying. Ishmael,
He's laughing because he's proud of you. He knows that he wouldn't.
For the sake of learning students.
I'm just trying. Wait.
So he's drawn a graph, two axes, and a straight line. So what parts of these two expressions are the same? We have limit as delta x goes to 0, which is the same in both cases, right? And the divided by delta x is also the same in both cases. So really what we want to show is that delta y is the same as f of x plus delta x minus f of x. That's the part. If we can show that, then it's clear that both are the same. If we show the two numerators are the same, then the whole thing is the same. Because the limit is the same and the denominator is the same. So if the numerator is the same, then both are clearly the same. So put 2 points on the line, any 2 points. And another point. And what are the, actually start with 1 point. What are the coordinates of this point? So you have a function, this is a function f of x. Everybody can help with this. What are the coordinates of this point? So we choose, at some point x, we choose a value x.
coordinates of this point and set x,
So what is the x value of that point?
x,
X. Okay. So you can start with, so you write bracket x. I can't see. X, comma, f of x. Perfect. So the x value is x. The y value is the function. Y equals f of x. Yes?
which way? Are we?
Is it clear that f of x is the y value of the point?
Yes, you agree. This is point. X value is x. Here.
And then let's add a, okay, so this is the y-axis. This is the x-axis. We choose a particular, we're using x kind of in two ways, but that's all right. Right? So this is the y-axis. So what is the y value at this point? It's just the function. When we draw a function,
Our function is f of x.
right,
Y value
the whole line
is f of x.
is f of x. Right? And what f of x tells us is, give me any x and I will give you the y value.
Right.
So then what is the y value? Well, it's f of x. Right?
Oh, the y value is
Yes.
For that point x. Yeah. Or in general. So then we can, that's why we sometimes write y equals f of x. Same reason.
Okay. Got it.
Love, we also,
So let's choose another point here. This can be x or x2.
so
But according to
for this, let's call, there's a distance here. We'll call this distance delta x. So this new point is x plus delta x.
yeah, x plus x. Okay. X.
X plus delta x. So we started, we have one point x. We're going to go, delta x is a distance, a difference, right? So we go some amount further.
So tell me the coordinates of this point. Like coordinates.
So
What are the coordinates of that new point? So that means what is the x value?
X plus delta x, comma,
Almost. F of plus delta x.
f of x.
So what is the x value here?
X.
Where are we on the x-axis? What is the value of this point? Is x plus delta x.
Yes.
Yeah? So if you're asking what is the function value for this input, then you have to say what is the function value of this, whoops, sorry, I didn't mean to erase it. X plus delta x. So what is f of this? X plus delta x. And then these are the coordinates.
That's right.
So let's use numbers to give an example. If you're doing exactly, this is good. And let's do it with some numbers. I think it will help. I wanted to keep this here, but we'll do it here. Okay. So let's take. No, I'll keep the whole drawing. let's say this is 3. F of x is, should we just take x or some other number, some other function? Straight line. Let's call it, let's just call it x. Easy. 2x. F of x is 2x. Okay, this line, to be a true, oh, it doesn't matter. So f of x plus 2, let's say. So this is 2. Then, if x is 3, then the coordinate here is 3, comma. What is the function here? What is the y value here? Well, 3 times 2 is plus 2, 8. So this will be 8, which is f of x. I put 3 as my x, so I put 3 as my x, and I get a number. Right? Now, I choose how much should delta x be. Don't pick one. Pick another. Delta x is some distance.
-4.
Make it positive for the purpose of this. It could be minus, there's nothing wrong with that, but just for example. 4, okay. This is not really to scale, but let's say this delta x is 4. So if I'm at 3 and I go 4, where am I? 3 plus 4, which is equal to 7. So here I'm at the point 7. 3 plus 4. Right? And so the coordinate of the point, 7, if x is 7, then what is f of x?
14 plus 2.
Okay, so it's 7, comma 16. Could I also write this as f plus delta x? So 3 plus 4, and then f of 3 plus 4. Would that be the same thing as 7, 16? Is 3 plus 4 the same as 7? Is f of 3 plus 4 the same as 16? Why not? What is f of 3 plus 4?
It's 16.
It is 16, right? 3 plus 4 is 7, f of 7 is 16. So this is the same as that. It's just written in a different way, right? So I have, this 3 was my first x, the 4 is my delta x, and now I have the function at x plus delta x. So I'm asking, what is the value? The function here depends on, well, what is the x value? The x value is x plus delta x. That's how I chose, right? That's what this is. So the y value is the function at this point, this value on the horizontal axis. So f of that value. So we get this, right? So now we're ready to look at this and say, is this the same as delta y? Delta x is delta x, no problem. Limit is a limit. As delta x goes to 0, as delta x goes to 0. So this part is the same as this part. So all we need is to show that this is equal to this. If it is equal, then both of these things are equal. Right? So now let's say, okay, this is the y value, f of x. Here, the y value is f of x plus delta x. So we have y2 is f of x plus delta x. y1 is f of x. What is delta y? Delta y is y2 minus y1. That's what delta y means. Yeah? So now we just plug in. So y2 is f of x plus delta x minus y1. y1 is f of x minus f of x And this is still delta y. And we have an identity. Delta y is the same as f of x plus delta x minus f of x, which is this. So now every part of this is equal to every part of this, which means they are the same thing. Sabrina? Mówicece? Mukuwicece? Mukuwicece, yeah? Where did I put the cap? Here, okay. So we wanted to understand why is the derivative of a constant 0. So I took us through to remind us all the steps. So we have a tangent line. We want to know the slope of a tangent line, because functions that are curved, you can't just look at it and say, oh, this point, and it's not a straight line, right? It doesn't have a clear slope. So a tangent line. But then you go, but a tangent line, I only know one point. How do I get the slope? So then we saw, well, we can take the limit of the secant, of the slope of the secant lines. So we did this. And then we showed I can write the same thing, just in a different way. But it's the same thing. This is not a new kind of problem. It's just that delta y is the same as this. This is how I get delta y, actually. Right? I take the function value here, minus the function value there. That is delta y. So I'm just writing it differently.
About tangent and second line, you say to find limit of second line as it approaches to tangent line is value of tangent line.
Okay.
Yeah.
Mm-hmm. The slope of the secants, as you choose different points, the slope of the secants will change. You'll get this sequence of values. The limit of that sequence of values is the slope of the tangent.
Yeah. Let's finish the rules.
Okay, so we're done with this part. And so we wanted to use this to now say what happens when my function is a constant. If f of x is a constant c, where I'm going to make a new graph. So there's two ways of doing this, really, and c is a real number, any real number. It can even be 0. C can even be 0. Okay? So I have a graph. This is the x-axis, this is the y-axis, that's the origin. And my function is a constant. So we say without loss of generality. So whatever we're going to do for this example is true for any example. We choose a number, this is y equals c, this value here, right? Whatever units you have, this is c. So without loss of generality, it means it doesn't matter. C could be 1023, C could be 0.05, C can be any number, right? It could even be a negative number. It's just some number. And the function is, we've already shown that a function equal a constant is a horizontal line, right? And a horizontal line, we have said, always has a slope of a horizontal line always has a slope of 0. It's everywhere the slope is 0. Yeah? And so when I ask you now, this is the function. When I ask you, what is the derivative function? What is the function that tells me the slope of the tangent at every point? So one is, when you have a straight line, you don't even need to say tangent anymore because it's a straight line. It has one slope everywhere. in this case, the slope is 0. So if I ask you, what is the slope at x equals 0.7? What is the slope for x equals 0.7? The answer is 0. What is the slope at, pick a number, 5.63? Let's take a more interesting number. The slope here is 0. How about over here? You don't even need a number, you know that m is 0, you see? Aha, we're getting somewhere. This is minus, I don't know, minus 12.049. It doesn't matter. It doesn't even matter what the number is, you know the slope will be 0. So what you've just told me is, Amgad, whatever number x you choose, this, pick any number, I will always give you the answer, 0. So, okay, my derivative function is 0. Yeah? So when you have this, the derivative of this is 0. Everywhere. Yeah? Because the slope of a horizontal line is everywhere 0.
First time you put a number like, let's say 8.
Uh-huh.
So it's still going to be 0.
So imagine this is, so if this was 0, 1, 2, 3, 4, 5, 6, 7, 8. That's what that would mean if we put 8 here. Okay, so we have 8. This is a horizontal line at height 8. What would the slope be? It would be 0, right? Everywhere. So the derivative would be 0. If I choose a different number, c, not 8, but 5.63, my derivative of the function, the constant function 5.63, would be 0. Okay, feeling good? So we have 2 rules now under our belt. Okay. So we have the, maybe I should, hold on. I'm going to make this a bit more clearly. So given f of x equals c, where c is a constant in the real numbers, then f prime of x is 0. Given a function of x equal to a constant, where the constant is any real number, then the derivative of that function is 0. That's what this is saying. Are we ready to go to the sum rule? Okay, so the sum rule is the question. Now, suppose for these ones, we're now going to deal with, actually, let me just rewrite this a little higher. So given this, f prime of x is nx to the n minus 1. So we're going to make a little division here. So we've got power rule and the constant rule. For the following, we now suppose we have not one function f of x, but 2 functions. Suppose we have f of x and g of x. So another function. They can be any function. Cosine something, exponential something, x squared plus anything. Okay? One function f, one function g. Now comes the question. Again, I'm taking a derivative, and I ask, what happens if I want the derivative of f of x plus g of x? What is this? Of the 2 added together. So I can add f of x plus g of x. Right? You can add two functions. You ever tried?